So I'm going to talk about adaptive information security in body sensor actuator networks. This is a very preliminary work that I'm trying to get into. Mark's gotten into already. I like your opinion on it, and if you have any interesting comments, that would be great. So the current model for wearable systems, that at least in terms of what's available in the market, is that everything is sensor only, in that the whole point is to monitor people and not necessarily do anything else with it. The data gets collected, maybe in a smartphone, or gets sent to the cloud, and then doctors can monitor and process that information and provide therapies or whatever treatments to the patients. So that's kind of the vision or the kind of focus of body sensor network research that's been going on for the past 10 years or so. In the last few years, this model has kind of moved on to more sensor actuator case, where you have sensors which measure your physiological signals or whatever, and send the data over to specific actuators which can then actuate treatment. The very obvious example, I would say, is a continuous glucose monitor that sends its measurements to an insulin pump, which then injects insulin if necessary. The advantage of this particular approach is that it makes, it's a whole health management approach. It prevents complications from ailments, whereas the previous case, it was more about detecting problems. This one is more about preventing problems, if you can. So given this particular sensor actuator model, now you can imagine that security becomes an even bigger problem than what it was for body area networks or body sensor networks. There it was all about collecting data, or if somebody tampers with the data that's collected, that's being measured, then the data that's eventually collected at the cloud or whatever it is may be erroneous. But in this case, there is a direct consequence associated with incorrect collection of data, because the data directly goes to an actuator and then it actuates maybe incorrectly or in an untimely fashion. So security, when it comes to BSANs, is more has a direct safety consequence. And in order to, it's not just enough to build these systems to be safe in a benign environment. It's actually imperative that we build them to be safe in a malicious environment, for lack of a better word. And as far as I see, security to me is a subset of safety. Without addressing security, safety for such systems, I don't think is, one can claim that such systems are safe. Well, that's all I'll say about this. So, okay, so the argument that security for BSANs, if you buy that argument, that security is important for BSANs, then one of the important areas where one needs to ensure security is communication. And we have seen a bunch of talks all day so far which have talked about communication security. And not surprisingly, since this field has been there for a few years now, there have been tons of solutions that are available for enabling secure communication in terms of authentication, key distribution, and so on. You have biometric-based approaches. The pros and cons of one was talked about like 2 talks ago. You have out-of-bounds signaling. You have a bunch of mechanisms that are available. In terms of asymmetric crypto systems, people have tried to implement ECC or identity-based encryption for body sensor networks. And all this enables some kind of key distribution. Once the keys have been distributed, you're going to have to do data communication. Now, that has to be secure as well. So in terms of these devices being wearable and portable, very small form factor, and so on, the security that these systems, assuming that these solutions are relatively secure, and they do a good job of keeping people safe as a consequence, the solutions are themselves quite expensive, because they add a considerable amount of transmission overhead, storage overhead, and the time required to generate the keys might be considerable as well. And on top of that, these solutions have always been thought of as, okay, one-stop solution. You implement one of these, whichever works best for you, and that's it. Nothing changes. I contend that such a static approach to security for body sensor networks, body sensor actuator networks, maybe I just call it wearable systems, makes life easy. Okay, for wearable systems of the future has a negative consequence towards the usability of such systems, because there is a cost to security. Everybody knows that in this room. And that cost is going to, if nothing else, you're going to deplete the batteries very quickly if everything remains the same. So think about it this way. If I'm wearing a wearable system of some sort, monitoring my glucose if I'm a diabetic or whatever, and I am a professor, so I do nothing else but sit in my room and type on a keyboard all day. How much malicious is that environment? Not really, not in my opinion anyway. I don't think my students are trying to kill me yet, but you never know, but hopefully not. And so why have such a complicated security solution built into it that's always running? It's unnecessary as far as I'm concerned. So why not tune the security that is being provided within the system based on the threat context that is around you? If you can measure the threat context in some meaningful way, then you can maybe make the available security within the system more secure, or reduce the security and when I'm sitting in my office. So it's basically making the system essentially insecure, but cheap, and therefore extend the life of the system in benign context, and making them more secure and costly in a malicious context. And the hope is that by doing this adaptive security, you will be able to achieve some amount of cost saving. So the approach to do that, as far as I'm concerned, is to have some kind of a threat context detector, magic. Suppose it gives you an information about what kind of threats exist around you, then you can select an appropriate security level for your system and then implement that and keep doing this over a period of time, like throughout the life of the device or whatever it is. And hopefully you will achieve an appropriate balance. So there are two things that we need to do essentially for the system to work. One is threat context detector, and the other is security level selection. In terms of threat context detector, the idea that we're trying to implement right now is to have a honeypot system for wearable devices. So you have honeypot systems like the darknet thing that they were mentioning. It's kind of a honeypot system that exists. People use it in the enterprise context where you have a very dedicated device that is sitting in one part of the enterprise, and if somebody tries to connect to it, then because it's usually using an IP address that nobody should connect to or whatever, that it's a bad guy, and therefore you try to interact with the bad guy to figure out what their capabilities are, what their intentions are, so on. So take that idea, apply it to wearable systems. Maybe you can have, your base station is quite capable, assuming, and you can have a bunch of other helper devices. We'll talk about that in a few minutes. And you can end up trying to figure out if, first of all, there are bad guys around you, and if there are, what are their intentions? What kind of attacks they can mount, or they at least intend to mount. And I'm not claiming that we're going to have, or by using the system, we're going to get complete information about the bad guys around you, but you'll get some information. And using that information, hopefully we can increase the level of security that the system is currently implementing. So in order to implement this honeypot system, this wearable honeypot system, there are two kind of approaches that we're trying out right now. The first one we call the bait method. Here you have the base station that is pretending to be a node in the network. And it is kind of an open device. So if there is a bad guy, whoever wants to, who's scanning the environment, it finds that this node is present and it's open, and tries to connect to it. If you connect to it, then the base station and the bad guy can start interacting with one another, and the base station can try to figure out what the capabilities are or what the intentions are of this bad guy. But obviously, this is not sufficient, because if the bad guy is more intends to kind of mess with the communication between the devices and the base station and do nothing else, like not interact with the base station at all, then this setup won't detect anything. So to overcome that, what we try to do is switch to what is called, have another mode called the message mode, where you have the base station and you have a bunch of helper devices. Now the base station and the helper devices have kind of a communication that is going on between them, which is relatively low security compared to, say, in an actual wearable system. So if anybody is trying to mess with this particular communication, and the idea is to make it seem like it's actual communication that may go on within the wearable system. So if somebody's trying to mess with this particular link, you can see that, and you can immediately figure out, okay, there is a bad guy. they are trying to maybe tamper with the data, maybe trying to replay the data, or whatever it is, and therefore we should be a little bit more careful. So at least, so that's that. And there is this high security channel thing that I was talking about, but I won't go into that details unless somebody is really, really interested. Okay, so the honeypot observations determine three things. One, the presence of adversaries around you, both passive and both. So bait mode and the message mode allow you to do that. The adversaries' capabilities with respect to the attacks they can mount. So the message mode allows you to capture some of that. And the adversaries' intentions with respect to the wearable system user, which is the person who's using it. The bait mode allows you to capture that. And given this observations, and now the next step is to try to figure out what appropriate level of security you might want to implement within the system. So the current plan to enable this is to devise a bunch of security levels within the system, within your wearable network. And these are characterized by two things. One is the number and type of protocol steps that you might want to use. I mean, whether you're trying to use some kind of a key distribution process, how extensive it is, how simple it is. And also, you can determine or you can define a different set of variables associated with the security primitives that you're implementing. So what kind of keys you're using, are you using nonces or not? Are you using some kind of an integrity protection mechanism or not? So all these is tweakable, and we can choose different combinations of these two characteristics to design a level. Obviously, the design of the security level has to depend on the environment of the operation of the wearable system, and also on the capabilities of the individual entities involved. It's not going to be the same for all wearable systems, and it's a very user-specific thing as well. So the next step, or the final step, I would say, is basically mapping this security level that you have defined with the threat context that is being observed. One way of doing that is take a very static approach where you build a table where you say that, okay, if the honeypot observes X, Y, and Z, this is the security level that I'm going to implement. The honeypot observes A, B, and C, this is the security level I'm going to implement. Very static-y, maybe appropriate for very simple systems which can't have many different types of security levels, can observe very little things, very few things with their honeypot. Perhaps that's good enough, but maybe you can have a more extensive system where you learn what security level to implement based on the honeypot observations that are being provided. And that change that over time in runtime. That'll be really cool if we can achieve that. All this is pipe dream so far, but pie in the sky thinking anyway. So to kind of sum up, basically what we're trying to do is to build an adaptive security solution for wearable systems where you have both sensors and actuators. We are trying to implement a honeypot system to figure out what's the threat context. We're trying to define security levels associated, which we can implement within the system and then map the two things together. Obviously, tons of challenges need to be overcome to solve this problem. The first and the most simple one, and the simple is the right term, but anyway, the most obvious one at least is there are a bunch of link layer issues involved in creating this honeypot in the first place. Because if you're using Bluetooth or some kind of technology like that, there are only, for every master there can be only, 7 odd slaves or something like that. So if you have a large enough wearable network, then there's not going to be an 8th node possible, which can act as a honeypot or an open node for the bait mode of operation. So you need maybe another Bluetooth stack or another antenna and so on. So I don't know if that's necessarily, this is kind of one obvious example where link layer issues play in. The second thing is that in the bait mode, you want to interact with the bad guy to figure out what they want. Now, how do you make this interaction seem legitimate? Bad guy should not immediately figure out that, okay, this is some base station trying to give me garbage, so I'll just simply immediately cut off the communication. So in that respect, I mean, even if that happens, at least we gain the knowledge that there is a bad guy who wants to interact with the wearable system. So at least that's some information, but maybe we won't get enough information about what their real intentions are. The third thing is that if the honeypot messages that are being exchanged, what kind of information is being exchanged in that? And at what security level that is implemented, so that the bad guys who are trying to interact or trying to modify those honeypot messages are not, they immediately don't figure out that they're being trapped. So that's important. In terms of security level design, coming up with the security levels is an obvious problem. In terms of, and also because you're kind of trying to use the honeypot to measure, to observe what is going on, and then apply an appropriate security level, you want to make sure that the system is stable, and that you don't completely keep switching between different security levels and just overwhelm the system. And finally, I'm making this huge argument about adaptive security and all that in order to save some cost associated with implementing security and making it more usable in some sense for the users. But deploying a honeypot, exchanging all these messages is going to add its own overhead. And having these different security levels associated or implemented within the system means that you're going to have so many more different components of security primitives implemented within the system. So if nothing else, it's adding storage space, if not more interaction and all those overheads. So there is a balancing act here. At what point this detection or this adaptive security becomes too complicated for, it becomes too complicated for being used in the first place, and at what is the right level at which we should use it so that it minimizes the cost of security is something that needs to be optimized for. So no conclusions. I think that's the wrong slide. That's pretty much all I have to say.
Peter Honeyman, University of Michigan. Can you quantify your security savings? I mean, you're characterizing the cost of security as being high, as being worth all of this effort. My experience has been those costs are actually minimal. In what context? In what context are they minimal? In what kind of? Well,
context?
I'm asking you if you've quantified them, if you have a context in which they're high. My context was, video conferencing, encrypting everything over the wire, and we turned on the crypto, turned off the crypto, and it made a 2% difference in throughput.
In terms of my experience, and at this point we're running experiments to get more detailed results, but in my experiments with modes and shimmer modes, for example, the cost of security was large enough that we had to actually disable it for some of the other projects that we were working on. That's where this idea for adaptive security came about. I cannot think of the exact numbers, but I can,
And you think that in that kind of limited computational environment, it's realistic to add on these bags on the side? I mean, which is cheaper, to just do the security or to have all of this detection framework? And
that's the point.
Yeah, that's the question.
That was the very last point that I made. That you could do this, but there is a cost, and so where is the trade-off? Where is the balancing line?
Hi, Mike Krishna from Johns Hopkins University. I guess my question was, is your honeypot, you referenced that it was a part of the base station. Is this base station also mobile? So does it move with you such that it's continuously communicating with your network, your body area networks, or sensors, excuse me?
Right. At this point, yes.
Okay. And had you considered any methods or have any intuition how you would handle traditional ad hoc network sort of attacks, like Sybil attacks and gray holes? Because traditionally these are sort of hard to detect because you're saying you report that you are a network that's supposed to be, or a node that's supposed to be in the network, and ad hoc networks just allow nodes to come in and out of the network promiscuously.
So in this case, your body sensor network is static. You have a bunch of devices that are talking to your base station. The base station knows which those devices are. It's not
like a traditional ad hoc network where nodes come in and then move out and new nodes come in. So the fact that a bad guy tries to come in itself is a problem. So you can detect that. At least the presence can be detected, if not more. So so it's not a direct association. I mean, I don't think there's a direct comparison like in the situation you described.
Okay, thanks.
Eugene Wasserman, Kansas State University, again. A two-part question, or two questions that just going to ask as one. The function, or the extent to which your students may or may not want to kill you, is probably a step function rather than a continuous function that changes around exam time. Which means that if you deploy all these honeypots, your students may already know what's going on anyway, so your adversary may have a very good idea of what the vulnerabilities are before you ever need to ratchet up your level of security. And the second part is a usability question. When you do ratchet up your level of security, for example, if anyone's visited their bank from a new browser recently, it may have asked them a series of other questions. Then there's a little thing that says, why am I being asked these questions? Right. Perhaps here, rather than lower or increase the level of security, it may be more useful to run the detection module, always run with a maximal level of security. When your detection module says you should ratchet up, you may want to give the user a heads up. Your students may be trying to kill you now, and not lower or raise the level of security at all.
So that's definitely another aspect of this work. So in terms of, if nothing else, you could just raise an alarm saying that, okay, something's wrong, get out of here, If students are trying to kill you, get out of your office, get out of the building, whatever, So that can definitely be another aspect of it. But I think it's complementary. I don't think it's necessarily one or the other.
Denise Anthony from Dartmouth. I just want to support the approach of adaptive security as a model in these environments. It's usually like the threat model is, the terrorists are trying to attack every system, including my glucose monitor, and I just think, we're in a room, we don't have an armed guard. It's because we recognize that this, not national security secrets, we're not exchanging proprietary information. We didn't think we needed an armed guard or an armored system, and it might actually not cost that much. I mean, I don't know how much an armored guard costs. It might not be very expensive, but the trade-off is because we recognize it's not the security environment, the threat model is not that high. Now so I appreciate the detection and certainly the cost difference between employing methods to determine if your security is going to be high. If that's as costly as having the armed guard or whatever, then we're not going to have any benefit. But I just want to support the approach.
Right. I mean, you can have user-specific solutions depending on if it's Dick Cheney. Then maybe you want to implement a lot of things irrespective of cost, and maybe it's me, then maybe you don't have to worry too much about it. So I personally think that having approaches is useful. To what extent, but the real trick is in tuning them, and that's where I guess most of the optimization of research work will go eventually into. All right, thank you. Yeah, thanks.